you for the invitation and thanks everybody for coming. I've been teaching this subject for, the first time I taught it was in 2017. Okay, so quite some time ago. And this is the largest audience by far I've ever had. Maybe it shows you that when I first started on this subject, it wasn't very popular. But steadily over the years, it's become more and more popular. So it's exciting to see so many people interested in that subject. And so I'd like to share with you a very condensed version of the course I taught before, with a particular focus on applications of problems in economics. So for those who are not economists here, such as myself, there's lots of other applications, which I'm sure some of the people in engineering and business will have come across as well. But I won't be focusing as much on those. I'll focus on economic application. I just want to say, so this is where I am, but I should give credit to, I'm visiting Harvard Business School this year. So I just want to recognize their support this year of my work. And I should also mention that I'm writing a book on this subject with Archis Gate. Archis is an industrial engineer. Maybe some of the IUR people know Archis. He's worked on this area for a long time. I have a couple of papers with him as well on the subject. And so we're writing a book. And so some of the things I talk about are really because of our joint discussion. So I include him as a collaborator on this. Okay, so let me start with the basics then. And I guess the idea of what the basics are is a matter of perspective. I'm going to, is everybody here familiar with basic real analysis? Everybody should know about topologies and interiors and all that. Who here has seen linear programming before? Not infinite dimensional, but just regular old linear programming. Okay, so that's good. So a few of you. So for me, and the viewpoint that I've taken on this subject is that the beginning is linear programming, so basic linear programming. And so for those of you who have seen it before, this is a review. For those who haven't, maybe you'll see it's a sort of a basic object. So this is the kind of problem that we're going to be looking at. Minimize linear objective function. So this is C transpose, this is the basic vector multiplication, the inner product in Rn, subject to AX less than or equal B. A is a matrix. X is a variable in Rn. B is what we call often the right-hand side, referring to the right-hand side of this equation. And this is in Rm. It's important that M not equal M necessarily. They could be different dimensions. And this object, sometimes called the constraint matrix, we refer to these things as the constraints, is a mapping from Rn into Rm. And we use the standard abuse of notation to refer both to the map and the matrix by the same thing. Okay. All right, so maybe somebody who's seen this before, where have you seen it before? Where does this kind of thing show up? Maybe to give some context and have some people talk. Oh, yeah, please. What's your name?
Antoine.
Antoine, tell me where you've seen it.
I sent it for the first time in the master class taught by Alfred Davidson.
Okay.
So we can use that basic method to solve optimal assignment problems.
Okay, and in an optimal transport problem, the A would have a very specific form, which has to do with some like matching in some way, and then you would solve this problem. Did you do the finite dimensional case or the infinite dimensional case?
I think it's finite dimensional.
Okay, so the finite dimensional is a transportation problem, and there's all kinds of algorithms to solve that. Okay, any other? Maybe we get one more example where you've seen it before.
I saw in yesterday's macro class, which we are trying to minimize the cost of production.
Okay,
Then the production, consumption we want to achieve.
okay, and it was linear like that?
Yes.
Okay, so it's linear, and how did you solve it? Did you actually solve it at all? Or you just set it up as a-
Like, just
Do
take
the
a
first order
direct-
condition of that. Oh, okay, interesting. Actually, this area, I should say, solving this problem is still a very hot area of research in operations research. Okay, so there's a whole bunch of methods to solve that. There's the traditional methods, there's first order methods, there's all kinds of things. So this is a hot subject in operation till today. But we want to do something a little different, and actually, we want to do something a little older. So the infinite dimensional version of this problem predates the finite dimensional version, if you can believe that. It's with Kantorovich. Kantorovich, who studied this, like this optimal transport problem, is actually the older version. But before we do that, there's a reason why I want to start with the finite dimensional version. Is the finite dimensional version gives you the right perspective about how to think about the problem. There's actually many views of the problem. I think there's at least 3 valuable views of how to think about a linear program geometrically. But I want to give 2 of them, which are more relevant to what we're going to discuss today. Okay, so the first view of how we think about this problem features the fact that a linear program, when I write it down, involves 2 vector spaces and the relationship between 2 vector spaces. So the way we view it, ax greater than equal b, I can interpret this geometrically to say that ax is greater than equal b if ax is in the shifted cone. Okay, so this Rn plus is the set of non-negative real vectors. And ax in b plus Rn is I take that cone and I shift it by b, and I need to have the mapping A go into that set. Okay. So this is how I like to draw this. So I like to draw them as boxes. Of course, Rn is not bounded. Okay, so this is just the schematic. So Rn maps, I take A, the matrix A, and I send it to Ax. And for this thing to be feasible, it needs to be inside of this cone. Is that everybody comfortable with that?
So can we RM?
Should be RM plus, actually. So it's got 2 typos. It should be RM plus.
Or would that too?
It should be M. Yeah, so actually, that's a very good point. This is actually one of the most confusing things about studying linear programming. You'll see actually for the full statement of the problem, you need to keep track of 4 vector spaces. And one of the most difficult things to handle when you do the infinite dimensional version is not only you need 4 vector spaces, each of those vector spaces could have different topologies on them. So there's like a proliferation of different issues that you could, and there's tons of modeling questions like which vector space, which topology on that vector space, and you'll see that as we go through the application. And so this mistake of having Rm and Rn, that's actually very common. And it's common conceptually to mix up these 2 spaces. So I'm going to use the language set in this book called Anderson and Nash. I want to call this the variable space. Okay, and this is called the constraint space. I think we're running out of space in the room, but speaking of spaces. Has anybody seen that particular perspective on the problem before? This is not the most usual perspective. There's a seats over here. Okay. Yeah, this is the variable space and this is the constraint space. But as you can see, this problem is kind of hard to see where the maximization is happening, right? Or minimization in this case. So the minimization, it's hard to see how C is acting. Okay, but this one is very helpful to see what B is doing. Okay. The other perspective has a slightly different point of view. And before I go into that, I just want to say that everything I talk about, I write it, this is like the standard form for linear program. But in fact, the most general problem that you can solve looks something like this. Okay. I think there's one more seat back there. So here I'm minimizing a linear function subject to, and now there's 2 kinds of constraints here. One is that Ax is related to B through this other kind of ordering. This is what's called a conic ordering. Okay, so K is actually going to be a cone. And X is bigger than 0 with respect to some cone C. Okay. Does everybody know what a cone is, by the way? You're nodding. So what's a cone defining for us? What's a cone?
So we have the vertex and zero, and then convex lines. Lines.
So that's the geometry of the cone. It's like this. It has a vertex. Well, actually, it need not have a vertex, but let's not get into that. This is actually a pointed cone. But actually, most of the cones we talk about are pointed. It has an apex and it opens up in one direction. Does anybody remember the algebraic definition? If X is in the cone, then alpha X is in, or lambda X is in the cone for all lambda bigger than or equal to 0. That's the definition of a cone. So sometimes they call this a conic linear program because there's cones defining the constraints, but in many ways, it's essentially the same theory as the standard one. The thing to see is that, what do I mean by this? It's again what I saw before. U is bigger than B in this ordering K if U is in this shifted cone K. Okay, and this is the way to visualize this problem. I like this very much because it tells you that there's 2 cones and 2 spaces. And as I said, in the end, you'll see these problems involve 4 spaces and 4 cones. And it's difficult to keep track of what all of them are doing. Okay, so I've kind of gone a little bit alphabetical. So C is in X and this K is in the constraint space. Okay, so C is before K in the alphabet, so I have it this way in the picture. Is everybody okay? Yeah, question.
Is there like a well-developed theory of these kinds of optimization problems where you assume this homogeneity, but you don't assume convexity of the problem?
Oh, I should say, yeah, well, there is, but generally, most of the theory is for the convex cones. So that's another, yeah, so typically they are convex cones. Okay. But there is a theory that they're just general cones and not even pointed cones. They can handle that as well. Any other question about that? Okay. Now, I like this view, and I think this is the view that helps you get everything in the right space. But there's another view that you see the action of C, and it also gives you a little bit of a viewpoint of the geometry of the problem. Okay, another perspective on it. Now this is not working. Why not?
If you're not assuming convex cone, is it still a linear programming program?
Yeah, you probably wouldn't call it a linear programming problem, but there are ways to handle it. Like if you introduce some conjunctions and stuff like that. So there is theory of that. There might not be space now in the room. Oh, there's one. Okay, yeah, there is. So the other perspective is what I sometimes it's called the row view. I like to call it the polyhedral view. Whereas I look at the problem in a different way. Now, one thing you'll notice is I actually changed the way that it looked. So here I had minimized C transpose X subject to AX bigger than or equal B. And when I go here, I've kind of shifted it around, maximize C transpose X, AX less than or equal B. That's another thing. When you first start looking at linear programming, people write down the problem in many forms and don't explain the reason why they do it that way. This way, maximize with a less than or equal to is the best way to understand it geometrically in this form. Okay, and let me explain why in a moment. In this perspective, I want to think about AX less than or equal B as a collection of a bunch of linear inequalities. Okay, so what I do is I take A and I write it down as a collection of rows. Okay, so here is the perspective that A is a collection of rows. So AX and A is going to be a collection of rows like this. There's M rows. And this is actually A transpose X up to AM transpose X. Okay, so this is, I think that's sometimes why they call this the row picture, is it's really looking at the row function of A. The other function, the other way to think about AX is that AX is a linear combination of the columns of A. And if you look at a linear program in that way, it actually gives you another geometry in the column space. Okay. But here I'm looking at the action of the rows on X. Okay. Now, here's an interesting question for you. And it's funny, when I started working on this, I had a very basic question. How exactly does this look? AI transpose X less than or equal BI. How would you draw that? So you guys all know what AI transpose X equals BI looks like. What does that look like? It's just a line, right? But which side do you shade, right? It's less than or equal. Do I shade below the line or above the line? If it's AI transpose X less than or equal BI, which side do I shade?
Not the origin.
Yeah, the origin, but then what if this has some negative elements and stuff, right? So you would check the origin. But, okay, so this one. Oh, actually, it doesn't, it's too bright. It doesn't actually show the shading. That's interesting. It's actually shaded below. And it's no matter what A is, like for instance, if A was here, it would still be shaded below. So kind of testing zero is hard when I don't know. If I just give you a general A without numbers, how do I know which side to shade? Actually, it goes to the interpretation of what AI transpose X means. Okay, so is everybody familiar with, there's a geometric interpretation of that. AI transpose X actually has this formulation. The length of AI, the length of X cos theta. Where theta is the angle between AI and X. Does anybody remember that? That's very helpful in optimization. So what does it tell you if,
Just quick question. Like,
yeah,
the origin is in it if BI is positive, otherwise it's not.
sorry?
If BI is positive,
Yeah,
then the origin should be shaded, otherwise not.
I guess that's another way to do it, right? But I guess that's one way, yeah. But this way, okay, let's think about the geometry, and this one is actually helpful for later understanding of how it works. So if AI transpose X less than or equal BI, you actually are looking at the vectors that have an angle less than or equal 0. Okay, so what you actually do, the picture looks like this. Let me just, can I move this door? Yeah. Oh, you can get in, sorry, yeah. I wanna get you out. So let's take an X0 that's actually on the line, okay? And let's take another X in the space. Right? Then we look at this angle X minus X0. Okay, and I'm comparing that to this vector A that's going out of it. So what it's saying is that so if A transpose X0 equals BI, right? So AI transpose X0 equals BI, because that one's actually on the line, right? Then what is this with respect to AI? This is X transpose AI. All right. Minus AI transpose. What am I doing? I'm confused now. Is this right? Oh, this should be less than 0, right? Oh, sorry, this should be less than BI, right? This should be less than BI, but this thing actually equals BI.
No, not the, yeah, okay.
Did I do it wrong? Now I got myself confused, right? Oh, yes. This should be less than 0, right? Yeah. So can I do it this way? Yeah, this is if and only if AI transpose X less than or equal BI. Yeah, that's the right way to do it. So the way to think about it is that it's the set of all points that have angle bigger than 90 degrees, because the cosine should be less than or equal 0. So the angle bigger than 180 degrees from A. Okay, so that's I've never seen that really in any textbook. Maybe you've seen it, but I haven't. As a way to geometrically understand what this is. Okay. But I think it's hard in this picture to see exactly where B is, right? It's hard to visualize where B is. But I told you that we can actually see C in this picture. So where can we see C? So if I take a bunch of these inequalities, and I know all the A's are sticking out like that, okay? If all of them are less than or equal, then all the A's are sticking out. Then how can I understand where C is in this space, in this picture? Suppose this is the optimal, suppose this is an optimal solution, X star. Then where's the C? The C is in the same space as the column vector, row vectors. They're all in Rn. So C actually lives inside this space. And the optimal solution is you take the direction C, and I keep going in that direction until I find the solution that maximizes in the direction of C. So actually, you can have in the picture, C should be here. Okay, geometrically. Is everybody okay with this? Now, that's not really much of an algorithm to solve it, okay, but I think that's the right geometry to look at the problem. Okay, very good. Now, why do we like finite dimensional linear programming? There's actually several things that are good about finite dimensional linear programming that we would like to take to the infinite case. One thing about finite dimensional linear programming is if the problem is bounded, an optimal solution always exists. Going back to this here, what do I mean by a problem being bounded? What do you think I mean by an optimization problem being bounded?
The feasible set is bounded.
Oh, that's the first guess. The feasible set is bounded. That's very good. Actually, that's the distinction I want to make. So if the feasible set is bounded, then there is an optimal solution in linear programming. Because it looks something like this. That's what our feasible set looks like if it's bounded, right? So this will have an optimal solution if I'm trying to optimize in a linear direction. But how about something like this one? Okay, it's unbounded in that direction. Is the optimization problem necessarily bounded?
Depends on the objective.
Right, so if the objective is in this direction, then it's unbounded, and if it's in this direction, then it's bounded. Okay, so in the finite dimensional world, as long as the problem is bounded, an optimal solution exists. But in the infinite linear programming case, that need not be true. It need not be true. I'll show you an example of that later. When an optimal solution exists in the finite case, that is, when the problem is bounded, at least one solution is an extreme point. So does everybody know what I mean by an extreme point? So if you look at this picture, what would you say is an extreme point of this? One of these corners, right? That's an extreme point. And why do you think an optimal extreme point always exists? What's your intuition for that?
Look like you can make it on the combination.
Exactly. So I'm going to optimize in some linear direction, right? So suppose I'm going in this direction. So this whole face here is optimal. Well, at least one of the extreme points is optimal, because every face is a convex combination of extreme points. This need not be true in infinite dimensional case either. Okay, so that's another problem. I'm not going to show you that problem because it gets to be very hairy at some point. And this is another reason why we really like finite dimensional linear programming, and actually, when it was discovered that this problem has a polynomial time algorithm, it was in like the front page of the New York Times. Okay, we found a polynomial time algorithm for linear programming. So there exists very powerful classical, really the foundation of operations research. A lot of the theory of the field is because of some of the discoveries around this problems, how you solve it. And as I will discuss in tomorrow's lecture, there's a very nice theory, a duality theory. And this is what I mentioned. I only show you 2 spaces right now, but I actually said there's 4 spaces, because the other 2 spaces come from a related problem called the dual. And for finite dimensional linear programming, the duality theory is very elegant and it always works perfectly and it has a lot of intuition. But for the infinite case, that doesn't work. So this doesn't work. This doesn't work. Well, this is out of order, so there should be this doesn't work. And there is a duality theory, but it's not clear that it's nice. Okay. So all of these we need to qualify, and this is where the subject becomes very messy topologically and analytically. The finite dimensional case doesn't need to deal with that. Okay, so what do I actually mean by an infinite dimensional linear program? What do we actually make infinite here is we replace these spaces, Rn and Rm, with infinite dimensional vector spaces. Okay, so that's the problem. So I don't like those ones. Otherwise, it's exactly the same. Okay, but we're just gonna, only thing we're gonna change about the problem is where X lies and really where B lies. Okay, where the constraint, what the constraint space is. And I want to talk about a few choices for those infinite dimensional spaces. The thing about finite dimensional vector spaces is there's really only one of them for each dimension. It's Rn. So every finite dimensional vector space is like isomorphic to Rn. But once you go to infinite dimensional vector spaces, there's actually infinitely many infinite dimensional vector spaces, not just based on dimension. There's really 3 categories that I like to think about, even though you could argue this one is a special case of another one. Sequence spaces. So this is the easiest one to understand algebraically in comparison to the finite case. So in a finite case, we have a vector x1, x2, up to xn. If I make it a sequence, it's just x1, x2, x3, and I just label forever, right? So what's a sequence? This one commonly shows up in many applications that involve dynamic programming, discrete time dynamic programming, because I make a decision now, one period from now, another period, so infinite horizon discrete, infinite horizon dynamic programming. This is the common space that you study. Does everybody know what this little LP? This is a test whether you took analysis. So what's little LP? Does anybody remember the space little LP? Exactly. So it's there's a whole hierarchy of spaces of the space of all sequences, and these are the ones where I take the p norm and it's finite. Exactly. Okay, there's another one, and this is the one who are real analysts. They would say sequence spaces are just a special case of this with counting measure. But I don't think that's the right way to think about it. I think it's better to think about it as an extension of the finite space. These are, well, there's whole classes of functions that can be decision variables. And the 2, I mean, there's lots, but the 2 that I've seen a lot in economic applications where the decision is either an LP. So this is a function that's integrable in the p norm. Or C, which is the set of continuous functions. Now I've introduced another set, and this can get very confusing very quickly. Sometimes people call this set X. I want to reserve X to be the vector space that we're optimizing over. This is the set that these functions are defined on. Okay, so let me try to write it. And it's probably, when you first see it, it's a little confusing. So an element of this, x is in, let's do the C one. Is a function from this underlying set omega. So omega is like the arguments of my function into the reals. Okay, so we can write x of, and sometimes people use t, because little omega looks like a w. This is an actual value of the function. This one shows up in many examples, and we'll see some of them in our discussion. So for example, in mechanism design, the decision is the allocation rule, which is a function, and you might model it as an LP function. In optimal transport, you will see that the continuous functions are the duals of the measure that you're choosing. Okay, so this will show up in the duality theory of measure problems. But probably a more basic one is optimal control. I don't know if optimal control shows up a lot for economists, but in engineering, it shows up a lot. Usually the control you're choosing is like an L infinity function or some type, which is a decision variable that you have. Okay, so there's sequences, there's functions, and then there's measures. This is the one, I'm putting them in this order partly historically for my own understanding. Okay, so when I first started this, I was an optimizer and I didn't really know much analysis. Okay, so I took like basic real analysis. But as you go farther down, it gets more and more messy in how much analysis that you really need to understand. Okay, this is the easiest one to understand if you just have finite dimensional intuition. By the time you're here, your finite dimensional intuition is totally shot. And they got this like Wasserstein, Riemannian space stuff, right? That you need to use to understand this. And so this one is very far from your basic intuition. So here is where the decision variable is a measure. There's really a lot of applications of that. So a classic problem of that is what's called the moment problem, where you're trying to decide like a worst case distribution, which shows up in robust optimization. Information design, you're probably deciding a measure or maybe a compound measure of some kind. Also optimal transport and decision variables are measured here. Now, one thing that is good about most applications in economics and in business applications is that this underlying set omega is compact. If that thing is not compact, you got to get another book out, okay? With all the crazy analysis. But if this thing is compact, that I'm defining both these measures and functions, then it's sort of like your intuition somewhat works, okay? If that's no longer compact, then, you know, then all kinds of weird things can happen, and I don't like that. And as another thing I should say is that the number of possibilities increases a lot as you go here. There's like if you get a book on functional analysis and measure theory, there's literally millions of different names for measures. Regular measures, Redon measures, these measures, that measures, and you get lost really fast. So, you have a question?
So if it's not compact, like you're referring to that continuous function or bounded continuous function on
Well, especially this one. If this thing is not compact, there's like a million definitions of measures that are all different. If it's compact, then every different measure you hear, regular, Redon, this, that, they're almost all the same thing. For continuous functions in optimal transport, I know they have these like CC infinity. It's like compact on some, you know. So there are ways to get around it, but essentially in the end, the argument is always roughly some compact thing that you want it to be defined on. Any question about that? So as you can imagine, Rn and Rm, this theory, it has algorithms, it's more computational. Once you go here, it's like you can't solve these things numerically anymore, and we're really looking for structure. But this is very expressive, okay? If you can model problems in these spaces, it's very expressive. And I think that's why there's increasing interest in the field of infinite dimensional optimization. Now, what is it that the real game here is what of my finite dimensional intuition can I carry over into these general spaces? And you should know what works and what doesn't work and kind of why. Okay, that's really essential to making progress in these kinds of problems. I will talk a lot about that, but the first thing to understand is what about Rn can I generalize to these spaces? Now, the problem, I think, when you work with Rn is Rn has so many properties that your intuition has bundled them all together that it's hard to figure out which of its properties you're using at any given moment. And I think one of the benefits of you start doing these more complex problems, you start to understand, oh, that's a geometric condition. Oh, that's a topological condition. Oh, that's a problem of condition of the inner product. You start to have a greater sense of all of the power that Rn has and sort of separating it out. So let me say a few things about that. One thing that Rn has is a vector space structure. What I mean by the vector space structure, this is your linear algebra stuff. So it has, I can take two components and add them together, it stays inside of the vector space. And what's interesting about that is that this is all you need to define the notions of convexity. Convexity is a vector space definition. Extreme points is a vector space definition. So the actual definition of an extreme point is a point that I can't write as the convex combination of any other point in the set. I'll get to that later. And there's one I left off, and it's probably one of the most essential ones. Really, the essence of especially the duality theory of optimization is something called a separating hyperplane. Okay, so if I have a set and I have a point outside the set, I can separate them with the hyperplane. And a hyperplane can be defined only with the vector space structure. Okay, so I can define a hyperplane. Well, I should, that's a little unfair. Both of these can be defined just as the vector space structure. For a separating hyperplane, I also need an order structure on the vector space. It needs to be an ordered vector space. In this case, we order Rn with the positive orthon cone. Okay, so I need a notion of direction in the constraint space to define a separating hyperplane. Okay, so one is the vector space structure. One I didn't even list here, which is the order structure. Okay, that defines bigger than or equal to inside of the vector space. Another thing people like about Rn is they have this ball topology. Does everybody know what I mean by the ball, like a ball topology? So in Rn, if I have a point X, I can define the topology is defined by the ball of distance, right? So I want to define points with respect to distance to other points. And what's nice about this topology is that topology gives you the right intuition about closeness in a physical sense, right? So this point is close to this point because, or farther from this point because I can put a bigger ball around it, okay? This is actually something that fails in certain infinite dimensional vector spaces, okay? So I'll describe that to you. So your intuition about topology related to closeness kind of breaks down, and I'll talk about that.
Sorry, what do you? Yeah, what do you mean by ball? Do you mean like it's known space or?
Well, I mean, like,
if it's known space, I can define a ball. Then like it can be nice or not nice.
well, what I mean, okay, I'll give you, so that's a little, I'm being vague here, but let me describe, okay. There's a very interesting fact that if you give me an LP space, okay, P not equal infinity, and I give you the non-negative cone, so LP plus, it's the space of all sequences with non-negative entries. This thing has an empty interior, right? Now that's a little confusing. So why do I say this idea of ball topology? Because you would think that, okay, so I have there should be a little neighborhood around that point which stays inside. But in fact, the topology in LP is this they're like long, infinitely large, the balls are not bounded. Okay, so the notion of an open set doesn't correspond to bounded sets. That's what I mean. Okay, so this this very kind of nice idea of point set topology, you have to let go of. Okay, and actually I see a lot, and I myself make a lot of errors in this direction. Okay, it's a major source of errors in intuitive thinking. Another one is in Rn, and that's the thing I was drawing over here with these angles. There's a notion called the inner product, which gives you the idea of things that are kind of orthogonal to other things. And you can do projection and all this. In general, you don't have that. Okay, so there's, if your reasoning is sort of, well, I can just project it onto that might break down in general. Okay. Now, I said, I actually had it here. Okay, so separating hyperplane theory works in Rn, but doesn't work in some other spaces. Okay, so this one we can always have. This one works because we're defining a vector space. This doesn't work. We need to adjust our idea of topology. We need to come up with different ideas of maybe about how projection and this notion of inner product and actually how we define the linear functions we need to think about differently. And this one works. Now, I said it didn't work generally. Well, because if you are in a vector space where separating hyperplane theory doesn't work, then don't do it. Okay? You don't want to do optimization in that space. And the most general space that has separating hyperplane theory is, and this is a major mouthful, it's a locally convex topological vector space. Locally convex topological vector space is the space that you want to work in if you're doing optimization. Now, I'm not going to give you a long lecture about what is a locally convex topological vector space. The definition itself can take like 4 pages, depending on what it is. But the way I like to think about it is a locally convex topological vector space basically is the space where the intuition I gave you works. Okay, so if you give me a convex set A, and I give you a point not in that set. In particular, X is not in the closure of that set. Now, what would you like to be true? So if I give you a convex set and a point not in the closure of that convex set, I would like to be able to separate it with a hyperplane. And I would like to be able to strictly separate it, meaning the convex set is entirely on one side, and that is entirely not on the same side as A. That's what I mean by strict separation. Now, this whole area of, when I first taught this course, I spent like 4 weeks on separating hyperplane results. Trying to figure out all the, it's very intricate, okay? So I don't want you to get confused. If somebody starts a paper saying, I have a locally convex topological vector space, the reason they do that is so that this theorem works, essentially this theorem. That if you give me a point and a point not in its closure, I can have a separating hyperplane. And this separating hyperplane is used to prove duality and all kinds of results. Okay, so you can look at the proof. If you tell me you're in a locally convex topological vector space, I know your proof is going to involve separating hyperplanes. Okay, that's like a general rule. Now, how do we get to locally convex topological vector spaces? I'm not going to give you the definition. What I'm going to give you is the standard way to construct one. And the way to construct such a vector space is to actually pair your vector space of interest with another vector space. This is the idea of a paired vector space. So now I'm going to have 2 vector spaces. But this W is one that I haven't depicted anywhere yet. Okay. This is the 3rd vector space. So vector space X and another entire vector space W are paired if there exists a kind of a binary relation between them, or I take an element of X and an element of W and send it to the reals. Okay, so the notation XW is actually sent, and we use this thing to define this result. Okay. Now, you might be thinking, sometimes people use this notation precisely for this. Have you ever seen that before? So this, in my notes and my slides, this is going to be a very general object when I have these square things. It need not be a transpose. It need not have the properties that a transpose has. Okay, it's just the evaluation of something that's paired in this way. Now, let me say what this thing needs to satisfy. For these things to be paired, I need such a binary relation. I take X and W, send to the reals. And the first thing, which is often not even stated, but it's implied, but I like to state it because it's actually maybe the most important one, is that this thing is actually a real number. Is everybody with me? Now, why am I stressing that? Because that's already here. So what am I worried about? I'm worried about this not being a number at all. That's one possibility. This is like in the, have you ever got not a number in the MATLAB before? It's just not a number, okay? It doesn't exist. The other thing I don't want is for this thing to be infinity. This is not the extended reals. This has to be a real number. And you'll understand what I'm talking about in a second. Okay, this is something you've dealt with a lot. Actually, if you take a course on functional analysis, I would say at least a third of it is about this. Does something actually evaluate to a real number, or is it undefined or unbounded? Okay, so it's a really important issue that I'm going to like sweep under the rug. The other property is that, and this is essential too, that this is a vector space and this is a vector space. So this thing better be linear. Well, what does that mean? It's linear in the first term and linear in the second term. Okay, so I don't know. Does everybody know what I mean by that? So x1 plus x2w is x1w plus x2w. Everybody okay? I'm just wondering, am I getting ahead of myself here? Hold on. That's what happens. You get too excited, then you. Oh, yes. Yes, that's good. This one is typically not difficult to satisfy because the things that we're used to seeing are bilinear. Okay, those are the usual objects we use in these settings. And the third one, this one is in a way almost technical, which is this condition has various names. It's called non-degeneracy. Some people, I've even heard it called some like duality condition, which I don't necessarily agree with. The one I like is separates points. Separates points is the one that I think makes the most sense, although I might not get into the geometry of why it says that. But essentially it says, if I have an element of this space W that sends everything in X to 0, that W better be the 0 of the vector space. Okay. Every vector space has a 0. This is the thing that I add to any vector and it doesn't change its direction. Okay, so because we have two zeros, that's why I'm 0x could be different than 0y. Or 0x and W, sorry. And the same better be true in the other direction. So if I have a W that sends, if I have an X that sends every W to 0, that X better be 0. This is a really important definition. Okay, so a paired vector space. And I want to convince you that it's something that you're pretty familiar with already, I would say. So here are the properties, okay, P0, P1, and P2. So let's take X and W to be Rn. Everybody with me? How would you define this? The pairing. How would you define that square bracket thing? It needs to be linear in both arguments. What would you do? This one, right? just this one. So XW is gonna be X transpose W, which is the sum, I goes one to N, XJWJ. Why did it satisfy that? Well, that's not difficult here because this number is always going to be real. I take some real numbers, multiply them and add them finitely, many of them, that remains real. There's no real issue there. Why is it bilinear? Because you can just see from here, right? And why did it separate points? A question?
So maybe just if the transpose is just one example of pairing aspect.
Yeah, there can be other pairing, yeah. Yeah, this is the, but typically we stick to the standard ones, but yeah, you're right, you can define something more general. So this is just one example. And why does it separate points? Okay, you can just, because if, you can set up a contradiction argument, right? So it just has the right number of matching elements, and then you can set up a contradiction argument there. Now, here's one that is not a pairing, and I want to understand why. So if X is Rn and W is Rm, with M less than M, and suppose I propose this to be the pairing. It looks very similar to that, right? Is this one map everything to reals? P0 is easy, right? How about P1? That's also, so it's actually this one that gets you in trouble. So why does P2 fail?
You could have a W where like the last components are like non-zero, and it would send everyone.
Exactly. So you could take W bar to be the, where this is in the N plus first location, and that sends everything to zero, right?
Might be equivalence class this out, like always satisfy the class property by creating equivalence class.
So can you explain more?
Just like treat everything that sends it to zero.
You could
as
probably,
the
yeah.
same object.
Yeah, you could do that. And actually, you're right. So when we, okay, you're getting ahead of me. The reason why we make this assumption is so that we can actually embed W in the space of the linear functionals on X. And if we don't satisfy that, then we have like a non-empty kernel of that map, and then we have this multiplicity issue. Typically, we try to avoid that. But this is this actually, for people who are familiar with algebra, especially, this really looks like a condition to make the kernel zero, right, of a particular map, and that's what I'll show you that it does. Okay, so these ones are relatively easy. How about this one? If I have LP and LQ, oh, I shouldn't have shown that, okay? That kind of gives it away. So if I have LP and LQ, where 1 over P plus 1 over Q is 1, and if you haven't seen functional analysis, you might be confused at this point. What's the pairing here? It's exactly the same as this, but I send it to infinity. And now you can really start to see where the issues come. And the issues are predominantly with P0, in fact. This is okay to be bilinear. This issue, as I said, there's infinitely many of both, so you can still do that same contradiction argument you could do here. You can't hide something farther than it was in here. So what's an example where I get into trouble with P0 if I don't make this assumption? Maybe I'll just do one quickly, okay? I'll just do one. Suppose I make the sequence X to be 1, 1, 1 forever. And I make the sequence W to be 1, minus 1, 1, minus 1. How about that? Then what is this? Xi, Wi, I goes 1 to infinity. What's that? It looks like 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever. But this is actually not a number. Because one way to think about it is to pair the ones and minus ones like that, and it makes it look like 0. Or if I pair this minus 1, this plus 1, this minus 1, this plus 1, it looks like 1. So it's actually not a number. So this is an example of a sequence that doesn't converge, right? Or a series that doesn't converge. That's why it's not an understatement to say if you study real analysis, functional analysis, a lot of effort goes into establishing this property, yes?
Or which P and Q do you have in mind here?
Oh, it violates that, that's the key.
No, I mean, these two vectors are not vectors in the spaces, right?
Exactly, so I'm just showing you that this naive sum, you need to be careful about what things you send into the sum. So these ones, for example, are both in L infinity, for example. So in other words, you can't pair L infinity with L infinity, you'll violate P0. This actually is related to this Holder's inequality. Okay, so that's actually how you show these things are finite. Okay, now that you've seen this one is relatively simple, and if you're clever, it's basically the same argument. The key difference here is that now you involve integrals in the definition of the pairing. So if you give me a function x in LP and w in LQ, and notice now I have this third thing, which is the argument of x and w. And I take it with respect to whatever this measure is defined to be, usually it's a Lebesgue measure, and I integrate the product of those two things. Okay. And this one, actually, why is P1 true here? Again, it's just because of the product for the same reasons of the previous one. This one is also the same. It has the same issue. This one is actually a little tricky. This P2 is a little tricky because you need to realize that these spaces are defined up to measure 0. Is everybody familiar with that? You take the space of LP, you actually get two functions that are the same up to a finite, a measure 0 set are actually the same function. So to actually deal with this, you actually need to make it bigger than 0 on some positive measure set, and then you can do the same kind of contradiction argument as before. Okay, so this one at first glance might be trickier than it seems. And it's really P0 that you need to show, and again, that's Holder's inequality. It's the same one as the previous one, essentially. Now, let's go to the last example then. This is the one that gave me nightmares, you know. This one is the hard one, I think. Well, it's hard until you've seen it a couple times. Because, well, let me say something, and this is an admission, and I'm sure you all know better than me. I don't know what in the hell the D means. Does everybody know what the D actually means? I don't, because this is where the notation becomes a mess. Okay, anytime starts defining measures and integrals, the whole thing is a mess. Okay, so this might look very odd to you because x is now a measure, right? I'm used to thinking of x as what the function f of x, right? But the decision variable here is a measure. And I'm taking this integral not with respect to maybe Lebesgue measure, but this general measure. Okay? And I'm setting up this integral in a particular way given this measure. Okay? And now w is just a function here. So, and you know, this is where the notation becomes a mess. Like, for example, you might see it. Well, I can't even tell you how many ways I've seen it, okay? Like an infinite number of ways. You might see it like this. Now, this one I kind of don't like because it makes x look like a function of t. But is x a function of t? No, right? Can I write, if x is a measure space, can I write little x goes from omega into the real? Can I write that? No, because it's defined on the subsets of that. Okay. So in a way, this notation is misleading, I think, in a certain sense, because it gives you the impression that x is a function of t, which it's not. Now, so, I don't know, but this is the standard way, and I don't, is there a better way to
I
write it?
think it's like x of dt.
Oh, you can do that way too, okay, that's another way. That's another, I've seen it like that too. Oh, x of dt. Sometimes that they put the d first. Have you seen that, where it's like d mu of f or something? I don't know, the notation is really confusing, and I often find myself not maybe doubting whether I know how it works. Now, why is this one bilinear? So you ought to be careful now. So this one wasn't necessarily so bad because it still involves this product, and I need to use the linearity of the integral in its argument, right? This one uses the property that the integral is both linear in this and linear in the measure. Okay, so it uses linearity in both argument and the measure here to get the bilinear property. I'm not saying that's easy, okay? So this one requires more thought. This one is also a mess, okay? Because what does it mean to say that a measure is zero? That's even more complicated than this one, okay? There's a lot of issues you need to deal with, but I'm not going to go into the argument for this one. And this P0, that one turns out to be really a mess, okay? And there's actually a whole theory of that. It's called Riesz representation theory. And if you get like a textbook on analysis, so for econ audience, the best is probably this Hitchhiker's Guide, the Alaprentice and Border Infinite Dimensional Analysis. There's just a whole, I mean, there might be a whole chapter on that. And I'll give you a table, like, if this thing is unbounded and this, there's like a million different relationships, but roughly speaking, and this is very, this one, I don't want to get into all that, okay? So generally speaking, you pair a measure with a continuous function. You can relax and you can do a bunch of other things, but definitely you guys learn that when you learn integration, even Riemann integration. If this function is continuous, then the integral exists. Okay? Of course, you can generalize. So there's this property that the measure and the function need to be tied together through this condition of integrability and measurability. And that's what you need for this integral to be a real number. Otherwise, it doesn't exist. Yeah.
I mean, what do you mean by the extend to like R of infinity? Because like the matter space doesn't like the variable is like state mode one, and you integrate like constants. If I can go to infinity.
Yeah, so that's what we disallow that. That's the key. So it's a real number. It needs to be a real number.
Yeah, but you just said, okay, never mind.
Was that?
I mean, you just said like, if it's continuous, I have a measure and that exists.
Well, that would measure, that's why a continuous function over a non-compact set may not work. But if you give me a compact set, continuous function over a compact set, then that will work.
Yeah.
Yeah. But it needs to be also a Borel, what do they call that? Borel measure or a regular measure to make it be a finite number. All kinds of weird things can happen, I agree with you. But the requirement is that whatever you do with this measure and this function, it better be a real number. If it's not, then this theory all breaks down. Does that make sense?
Yeah.
Yeah. Next question?
It seems all examples can be summarized as you first give me a Banach space and then take the dual space and then take the dual pair. Is that a general rule to construct area?
No, it's not that easy. But I would say that in the econ examples that I've seen, it's always like that. Yeah, but there are other examples that are not like that.
That's sufficient, not necessary.
Yes, yeah. Yeah, this is much more general. Yeah, so what you might be thinking, oh, I just take, well, let me show you. Okay, let me show you an example. Okay, before I do that, let me just give you, so is everybody, so this is like some very heavy like functional analysis stuff, and you might be thinking, look, do I need to read all of Al Prentice and Border to figure out what's going on with this? And kind of you don't. You just, I think what I like to do is my intuition is still roughly here, okay? And then I just learn the necessary assumptions for this to work. Okay? And every time I work on a problem, I look at Al Prentice and Border and figure out the necessary assumptions I need to make, and then I put those into the model setup. Okay, that's probably what you're gonna do. That's the rough intuition, how you get these things to work out. And why do I say that is because now this is very untrue and very rough, but here's how I like to think about it. So in the finite dimensional, I don't know why it's not shaded in. Okay, so this is what it looks like. The things that are sticking out in this picture are what? So in the finite dimensional version, I have the problem in Rn, and these things are vectors in Rn, and that's because Rn pairs with Rn. Does that make sense? So when I look at something like this now, I have a function that's in sequence space. I can also make it roughly look like that, but what's sticking out here is the W. So I have this vector W that's sticking out of my set that's defining this inequality. That's what I'm thinking about geometrically. So if I have this one, and I like to call that thing I like to call it the normal vector of the constraint that defines my space. So what's the normal vector in a problem where the inequalities are defined with something like that? The normal vector is the W. So you kind of just learn to ignore the integrals a little bit and think about it like that, and think about this as just this. Does that make sense? And then this one, I think, is the trickiest. So if I'm in the space of measures, the linear inequalities that are constructed in this way have the vectors W, which are functions. But now it's really not in the same space at all. You can't really think about it, but I think, roughly speaking, this gives you the right geometric intuition of what's going on. So just because the spaces are defined in a weird way, don't think that this is not important understanding at least a little bit of what's going on. Okay. Any question on that? Okay, good. Now this is where it gets a little messy for a little while. So my apologies for this one. Because unfortunately, we need to define a topology on these spaces. Okay, so I have a vector space, I have another vector space, and I'm pairing it with that space. I want this pairing to induce a topology on my vector space. Is everybody with me? So my decision space, I want a topology on it. The reason I want a topology on it is all my existence results involve compactness in the topology in the space. Okay, so how do I do it? So the first thing about this pairing is P1, which is the bilinearity, actually says that every element of W is going to give me a linear functional over X. Okay. So here's a quick definition. I actually define the algebraic dual of X to be the set of all linear functionals over X. When I say linear functional, everybody hear me? Functional with an AL at the end. That means it maps to the reals. So a functional is something that always maps to the reals. So this is a linear functional. So the space of all linear functionals over X is called the algebraic dual. And I think this is where all the names, dual, everything of optimization comes from. It's really, this is the beginning of the idea of duality. Now, P1 tells me every element of W maps to an element of X prime, which is a linear functional over X defined as follows. It maps X to X with the argument W. So this is some algebra stuff, okay? So you're gonna get stacks of relationships of functions. And for people who like algebra, Rajitesh, I think, already said this is where you made the point already. because I assume P2, which is separates points, this mapping here is actually a one-to-one mapping. If you remember, a mapping maps, it embeds W into its domain mod the kernel. Okay? That's a property if you study like module theory or whatever. So if it's one-to-one, the kernel is just zero, so this is mod the kernel zero, just the original set. So what I can actually do is I can embed W inside of the algebraic dual of X. That's why I assume separates points. And this is the classic example. X is paired with W, and that's exactly what we do. So in this picture, the reason why A is in this same picture Rn is precisely because Rn is dual to itself. So I can draw it in the same space. But in general, I can't. Okay, in general, it's in a different vector space. But this tells us that I can take this thing I paired X with and embed it into the space of linear functionals over X. Is everybody with me there? Now, here's the topology. This is, okay. They define it as okay, this is also one of the most abused names in all of functional analysis, without doubt. You start putting stars and double stars and, it's just like, okay, what the hell is it? Tell me, a weak topology it's a topology, it's the smallest topology that makes a given set of functions continuous. That's what the weak topology is. You have to tell me what the space is and tell me what the functions are to define a weak topology. Otherwise, it's just a word salad, okay? This notation I like a lot. This comes from Anderson-Nash. What this is saying is the weak topology on X. It's the topology that makes all of these these are functions defined on X, right? It makes all those functions continuous. And it's the smallest topology that does that. Is everybody with me? Okay. So if you remember, and this is another thing that's easy to forget. If I define a continuity of a function, it involves the topology of both its domain and range. It involves the topology of two spaces. So the topology on X and topology on Y, and it's continuous if the inverse image of open sets are open. Now, let me just give you an idea of what the weak topology looks like. Okay? Because I think the weak topology is a very instructive object. Now, so what we have is we have linear functionals from X into the reals. These linear functionals look like this. This is for some W in the space W. Okay, that's what our linear functionals look like. Now, if I want to say that this thing is continuous, right? I need to take an open set in the reals and say that that's open inside of X now. Now, what does a typical open set in the reals look like? An open interval, right? So what I want to do is I want to look at the inverse of an open interval. Now, what is that? This is actually the set of X such that this thing is strictly between A and B. Right? But this thing is a linear function of X. So what does this set look like? It looks like something like that. I have a linear function between two elements. So that's going to be like this kind of the space between two parallel hyperplanes. And in fact, this thing is a subbase for the weak topology. Who here is a topologist? What is a subbase of a topology? Does anybody remember? So a subbase is you take all finite intersections of that, and that's a base of the topology, and the base is I take all countable unions of those. So what does that tell me? What would be a finite intersection of these? It's a polytope. So the weak topology is the topology that's based on polytope. They're actually zonotopes. Okay, for people who've done because they have parallel opposite faces. Okay, this is something called a zonotope. And I think this is one reason why weak topologies show up in linear programming, is that the underlying topology itself has a linear structure. Okay? The underlying topology itself has this this polyhedral structure. Now I should say something about this. Okay, the weak topology is not like a ball topology, because imagine you're in infinite dimensional space, and I take the finite intersection of those. Okay, if I have infinite dimensional space and I put finitely many constraints on it, that set's always still unbounded, right? So these open sets are unbounded. And the name they actually give them are barrels. They call them barrels. So this is a weird thing. In the weak topology, there is some direction in your open set that you can be infinitely like far away, if you like, but still close. Because the actual open sets are these barrels. That's what I meant before about the ball is not the right way to think about such topology. Is everybody roughly okay with that? So yeah, if you don't know what a subbase is, you can look it up. Now, if you look at another thing I will say, okay, I've been thinking about this thing for many years, since 2012. Okay? If you read Alan Prentice and Border, he's going to talk about seminorms and all these things before you get to this. I think this is the easiest way to understand what it is, but it's hard to find somebody to think about it specifically. Because a lot of the discussion of these topologies are for many other reasons other than linear programming. I think this one is the most valuable from the perspective of linear programming. Because it has a linear programming structure in it, if you like. Okay, does everybody understand? So if I wrote, what's interesting is that you can do the whole thing in reverse. You see that? So I can have W here, and I can have the whole thing in reverse because it's a bilinear thing. Everything I do to X, I can do to W. So the last thing I want to say in this little section, this is the last definition here. So remember I had the algebraic dual, which is the set of all linear functionals over a space. What I can do is I can restrict that space to be the set of linear functionals that are continuous in a given topology. So that's this notation. I take X prime was a set of all linear functionals over X. Now I take all linear functionals and I restrict them to those that are continuous in a given topology tau. Okay, and here's a theorem. I won't prove that. Actually, it's not so difficult. Is that if I take the space of all linear functionals that are continuous in this one, that's isomorphic to W. One direction is very easy. It's just from the definition. The other direction you think a little bit about. So what have I done here is, this is the beauty of the paired thing actually, is what I've done is I've introduced a new vector space that gives me, I embedded that new vector space into the dual space of my vector space. Okay, that's why it shows up in optimization. And I'll go back to your point, okay? So now you start to see where things are very complex. Now, so far, I haven't talked about the norm duals. And not every pairing in weak duality actually comes from the norm duals. Okay, so let me give you an example. L infinities, I take the space of linear functions over L infinity. Okay, then I restrict those to be those that are continuous in the norm, the standard norm on L infinity. That's isomorphic to L1 plus a mess. Is not L1. Okay, I'll give you a simple example of this. Okay. What you need to do is L infinity with respect to the weak topology of L infinity with L1. That is L1. And I get rid of this mess. Does that make sense? This is a very subtle point. If you go the other way, so let me write it down.
What is PFA?
I'll tell you in a second. It's a mess. Okay, you don't want it. Anytime you see this, make other assumptions. Okay, don't deal with them. I have a paper on that. It's a mess. Get rejected multiple places. Yeah, you know the story. So the other way is easy. So this is true. L1 star, its norm, its usual norm topology is isomorphic to this. Oh, by the way, sometimes we put the ones in the bottom, sometimes the top, that's also no consensus, okay, and I do that myself. Especially when there's a star here. Maybe that explains it. What it's saying is that L1, that should be L1. So if I take L1, the space of linear functionals that are continuous in norm topology is equal to the space of linear functionals that are continuous in the weak topology. Okay, in that sense, you can do what you said. Okay? But you can't always just take a problem in its norm dual and then make a pairing that makes sense. So the problem with this one is this is a mess. And let me give you an example of why. Okay, so let's talk about this PFA for just 1 second. This is a very interesting thing that I never really realized how important it was until I was in this like very dark alley. What's the definition of a linear function? What's the definition of a linear function? So you give me, okay, let's define a linear function. Let's say between X and Y, it doesn't matter.
Anyway, does that equal to L infinity?
Yes, and this is isomorphic to L infinity, exactly. Yeah. This is just by this theorem, but this one just happens to be that. So what's the definition of a linear function? It has two properties, right? We have the addition property. So a function is linear if it respects the underlying properties of the vector space itself. So if I take phi of A plus B, this will be phi of A plus phi of B, right? And the other one is lambda A. So then this is lambda phi of A. Okay? Now, the real question is, what about this? What is that equal to? Is this equal to this? And in general, it's not. This is actually something, when you study measure theory, this is an issue you deal with. It's called countable additivity, right? So if I have a measure, I can have finite additivity, but this countable additivity. But it turns out to be true of any linear function has the same issue. This is the definition. It does not imply this. But you don't ever want to deal with ones that violate that when you're doing optimization. Okay, and this is purely finitely additive. It's purely finitely additive. Okay. And you might say, well, who would ever come up with a purely finitely additive linear function? That's ridiculous. But let me give you one that's actually not weird at all. Can I define the set? It's actually mathfrak C, if you type it up, is the set of convergent sequences, okay? Are you with me? This is a set of convergent sequences. So I can define a function which is the limit, which sends C into the reals, which takes as an argument a sequence and sends that sequence to its limit. Are you with me? So I have a sequence and I have the limit of the sequence. And probably something you learn even in like your first mathematical analysis, like what a Rudin class, baby Rudin. This is true, right? That's true. As long as X and Y are both convergent sequences, and same with this, right? But the limit sequence is not countably additive. That's a beautiful thing, right? It's not beautiful, it's the opposite of beautiful. Because you take a sequence like this, like 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, whatever. Each of those converges to 0. But if I sum them all, I get 1, 1, 1, 1, 1, 1, 1, 1, 1, which has the limit 1. And now you can actually see the difference here. This thing, 1, 1, 1, 1, 1, 1, it doesn't converge in, well, I have it backwards now. It doesn't converge in L1, but it converges in L infinity. So that makes this thing continuous in this space, but not here. The problem is, of course, that L infinity, this isn't a linear function over L infinity because not every sequence is convergent. Okay, but there's actually a weird generalization of this limit function into this space, which has a similar flavor. Yeah, question?
What is isomorphic mean?
Isomorphic as a vector space. It's a vector space isomorphism.
Okay. Yeah. So nothing like preserving anything topological.
No, it's just the vector space isomorphism.
Sorry.
Yeah.
Yeah, I also have a question for Kiran. Like,
Yeah.
do you need P2 for this?
You may, maybe not, but I wouldn't want to try. Maybe not.
So how do
Yeah.
you define vector space isomorphism?
It's just, because this is a vector space, and this is a vector space. And if I have this isomorphism, like if I have X maps to X prime, Y maps to Y prime, and X plus Y maps to X prime plus Y prime. It's just it respects those. Sorry for the long diversion into the topology, and this is a kind of the worst it gets. But I think this example, that's why I like, although you say, I don't want to deal with sequence spaces because there's no econ application or whatever. I forget that. The sequence spaces are helpful for remembering the counterexample. The counterexamples are usually clearer in sequence space than other spaces, and I think it gives you the right intuition. Okay, so I really highly suggest studying, understanding the sequence space examples when you can. Okay, so what it actually gives rise to is all of that work to pair the vector spaces. I'm now going to endow my problem with a topology. That's the right kind of topology to make my theory run. Okay. So suppose I have a vector space X and Y, and sometimes we pair them like that. So X and Y are a pair of vector spaces that have the pairing given by square brackets. At the beginning, it doesn't look like I necessarily changed much, but I do know that this linear form I'm going to take with the pairing with W. So now C is going to be in W. Okay, and I'm going to use this as my linear function. The implication of that is I've made this function, the objective function, continuous in the weak topology. Simply by writing it like that, I made it continuous in the weak topology. Okay, that's the genius of it. Okay. So C is in W, as I said. I'm going to introduce a new notation, and this is very important to realize in the end, there's going to be 4 spaces. Now I have 3 spaces. The decision variable is in X, C is in W, which is paired with X, Z, I'm Canadian, so I say Z. All the things are, it has nothing to do with W, X, or their topology. Z is a whole other thing. Okay? I can't stress how important that is. This is like a whole other it's a whole other world. And it doesn't really show up until you get to duality, actually. So when we get to duality, we'll get to a lot of properties on Z, but it has nothing to do with the topologies on X and Y. It's a totally separate issue. B lies in this space Z, okay, which is the constraint space. K is a cone in Z. So you remember this K is next to B, that makes it a cone in Z. C is going to be a cone inside of X. I call this, how much time we have? 15 more minutes, right?
17.
17 more minutes. I'm a little stuffy. Let me open the door. If you look in the literature, exactly this kind of setup is what you might see as a general conic LP. I call it a paired linear program because that emphasizes the underlying topology of the problem. It's coming from the pairing. You could call it a paired conic LP. Conic is emphasizing the geometry of the problem. Pairing is emphasizing the topology of the problem. Both of them are important, as we'll see, to get the structure of the optimal solution. Interestingly enough, there's a paper from 1953 from people who know the history of operations research, which is very early on, about problems of this form. 1953, before a lot of things happened in optimization, they had defined this problem. And just to give you an example of how I think about things geometrically, because you have the pairings, there's also a way to think about A as a collection of things that are coming from the pairing W. And this is actually making these functions continuous. And if this is continuous, this mapping is continuous, there's a sense in which you can get the space, the underlying feasible region to be closed. So if your functions are continuous, then you can get closed in the constraint space. Well, I'll talk about that later. But if you do that, if there's only finitely many of these, then I need to take the constraint space to actually be finite. This is actually a very common example where I have a lot of topological structure on the decision space, but a relatively simple constraint space. So let me give you just a couple of examples of that. If you're going to take a takeaway from the class today, I think this is a good one. This is all the spaces, and these are the pictures. This is the variable space, constraint space. And actually, when we come later, this is actually the constraint space of the dual problem. We'll come to that later. And this comes from the pairing. And now, remember before I had C here in the first picture? Now C is here. Because in finite dimension, X is equal to W. They're both equal to Rn. But now that they're through this weird pairing, it could be a totally different space. So C is down here, X is here, and then there's this whole separate world in the constraint space. If I put the pairing on it, it's natural to think about the weak topology of this space now, coming from this pairing. And if I take the specific example where A is this set of matrices, then I also have a bunch of row vectors, if you like, that are also in this space of the dual space. So let me just, this is a little kind of a review in a sense. I've studied a lot of problems like this, and Archis, who's my collaborator on this project, he's a specialist in this question of countably infinite LPs, would show up in like non-stationary MDPs. I've simplified a little bit. I'm only taking finitely many constraints, but you could also have countably many constraints as well. So let's think about this in light of the pictures, okay? So what is X here? Well, that's the problem, right there. You have many choices. Right there, you see part of the issue of this, and this is, it brings my blood to a boil when they do it like that they don't tell you what space X is in. That's very common. For finite dimensional optimization, you don't need to have the little X in Rn, just get rid of it. But for an infinite dimensional problem, it's hugely significant what space I put this in. Because if I put this in LP, then that puts restrictions on C and A. Otherwise, these sums don't make sense. See what I'm saying? So if I make X to be LP, then what is W? It's automatically LQ, which is 1 over P plus 1 over Q. Otherwise, I can't even write down the problem. Now, what's really interesting about this is that what it takes to write down the problem for it to make sense by this LP, LQ automatically makes this constraint continuous in the weak topology. That's a good thing. And also makes this side of this optimization of these constraints to be continuous in that same underlying topology, which is also useful. Now, what's the constraint space here? There's only finally many constraints. Ignore the cone constraint, it's just these. That's going to be Rm, as I have m of these. And this one's a little tricky. So remember, K is the cone in the primal constraint. Okay, so the cone in this constraint space over here. And it's an equality. So that actually means that the cone is 0. Okay, so if you work it out, so in equality, this corresponds to a cone that's just a single element 0. And that's a cone if you look at the definition. And then what's the cone in this space? Sorry, what's this cone? That's just the non-negative cone, right? So it's the LP plus, so the set of non-negative. Okay, very good. Now let's do one that's a little harder, okay? So you look at this one. Here, okay, so I said not telling me which constraint space it in brings my blood to a boil, but I'll tell you what really brings my blood to a boil. You don't write anything there. If I don't write anything there, I mean, maybe I don't have that, it's this. It's kind of hard to tell what's going on, right? And you're not used to thinking of the measure as a decision variable, are you? Maybe if you do a lot of optimal transport, you grew up in that world, maybe. But for everybody else, it's kind of weird, right? Okay, so we want to think about this problem in this kind of a picture. That's our mapping view, and this is the kind of row view. So what is X? I kind of gave it away. It's some space of measures. And depending on what I assume about this, it'll have Borels and that, whatever, various qualifications of what the measure is. And so that thing, as we know, is paired with continuous functions. So I'm now that as soon as I put it like this, it kind of restricts this, right, of what it could be. Of course, you can get around that with additional arguments, but for the basic theory to work. And this, I have finally many constraints. I didn't use M. Why didn't I use M for the number? Because typically this is the actual moment of this distribution. So if you think about this as a probability distribution, these M are the moments, right? So this is RQ. The K is 0 again, and then this is the set of measures. Yeah, what are the set? Oh, that's something. I've actually been misleading you for a long time. I call this a space of measures, but it's actually not. Okay, I misled you for a long time. Because the space of measures is not a vector space. So this is actually what's called a set of signed measures. So they are signed measures. They can possibly take negative values. And if I take the positive elements of the space of signed measures, those are the measures. Okay, so this is a moment problem that's well studied in a lot of optimization literature and other areas as well. Okay. Yes. Any questions so far? So that's a lot of topology and we're gonna be less topology. Well, actually, that's not true. There's topology here too. So here's our problem, just to review. Okay, I have a three-space view. I have the constraint space, variable space, and the paired space with that. And now what I really like to do is to think about when an extreme point of this set exists. Okay, that's going to be the main result of this section. Of what we're going to discuss today. When does an optimal solution exist? So does everybody know what I mean by when does an optimal solution exist? You can write this problem and it might not even have a solution at all. There is no optimal solution to the problem. That's one other thing. You might see problems also written here with an IMP. I don't know if people have seen that. That's when they admit that they don't know if an optimal solution exists or not. But you can also see it written with a min, even if I don't know the optimal solution exists. So just that's a refresher. And then what we would like to know, one is existence, and the other is when is that optimal solution? When is one of them, at least one of them, an extreme point of the set? Yeah, question?
Is it legal to declare the meaning? Like it's as if I write the limit of the sequence even if I look at it.
I've seen it. I've seen it. Yeah. I have a funny story. So my son is named Max. So then I write Max all the time. And then we were, like this is a really math joke. Before, when my wife's pregnant, but before Max was born, we called him Soup. Because it wasn't attained yet. Okay, that's a really bad. Okay, so here I have an imp, okay, just for you, okay?
Was your wife okay with it?
Yeah, she's a math person too, so she has a master's degree in math. So the main result, and this is just generally true, and I hope everybody knows this result already, right? That an optimal solution exists. This is the Weierstrass theorem, and I don't think there's really any other theorem. You can weaken it. Okay, you can get compactness of the level sets and all that. You can find weakenings of it, but essentially it's a compactness and a continuity condition with potential weakenings. Okay. So the main idea of Weierstrass theorem is that there's two properties. So this is a general optimization problem. F is the objective, little f, and then big F is the feasible region. And I need to have a topology on the space. Okay. And it has two properties. F is continuous in that topology, and the underlying feasible region is compact. And the key thing is compact in the same topology. Okay, that's the. Now, when you first saw Weierstrass theorem, you might not have thought that as a practice of the working theoretician, the real thing that you need to do is to decide tau. That's the real, I need to figure out which tau I need to use. Actually, that's part of the action of the Weierstrass theorem, because there's multiple taus. I could use LP, L infinity, L1, space of, a whole bunch of choices for X, which has its own inherent topology. Should I use the norm topology, the weak topology? Which topology should I be using? Okay. The key thing is that they should match. Okay. So, and I actually prefer this. Another thing that makes me really upset. You have a problem, a linear program problem with those four spaces, and they say this function is continuous, this one, without any qualification. Without even defining what space you're in, it's continuous. Well, that's very underdetermined, right? Then it's really like, okay, you fill in all the details yourself. So I advocate saying tau continuous because there's many choices for tau. Now, there's something really interesting about Weierstrass theorem is that it shows an inherent tension between in the topology. If I, how topology works, if I keep adding more and more open sets, it makes things more and more continuous because continuity is based on open sets. But if I allow in more and more open sets, I have more and more open covers that I have to defend against to define compactness. So there's an inherent trade-off between continuity and compactness. Okay, and that's the thing you want to keep in mind. And this is another reason why weak topologies are very common here, because weak topologies are the minimum thing to get continuity. That's how they're defined. And so that is the easiest to establish compactness, because of the minimum to get continuity. And this is the general comment. If you're working with the definition of compactness, like I'm looking for open covers, you're dead. That will never work. There are some very powerful compactness results, and actually Wikipedia is our friend. There's just a list of compactness results. And if you do work in this space, this is usually the hardest thing, is to show compactness. Okay, and here are a bunch of results. I'm going to talk about Arzela-Ascoli, Banach-Alaoglu theorem, Helly selection theorem. These are very common. I'm not going to talk about Prokhorov's theorem, but that's used in optimal transport, but I'm not going to cover it in our lecture today. But as far as I've seen, those are the 4 most common. Some of them you might see is the simple, what's called the Tikhonov theorem, where you have compactness in each component, and then you take the product of that. So Tikhonov theorem also shows up. Okay, so let me just give you the Banach-Alaoglu theorem, and then we'll break and we'll come back tomorrow or 2 days from now. Banach-Alaoglu theorem, you're going to like it. So here, I think in the optimization papers that I have read, this is the most common way to show compactness. In some of the econ literature, it's more common to use some of the other ones, which I've only learned more recently. But this was the workhorse for most of my thinking. So the Banach-Alaoglu theorem is very powerful, but it has a very misleading structure, I think. So what you have is you have 2 normed vector spaces. So you start with Banach spaces, essentially. X and W are Banach spaces, normed vector spaces. And I have it that X is paired with W. And is that the right way? Did I screw it up? See, I might have screwed it up. One of them, okay, is precisely the embedding with its norm topology. So you see that? So this is the norm topology of that. So let me see if I did it correctly. So I'm saying X is L infinity. Yeah, this is right. Yeah. So X is L infinity. And I can pair X with L1. And if I take, and that's what I wrote here. What I wrote here tells you that W is actually isomorphic. The W with respect to its norm topology is isomorphic to L infinity. That's what I wrote behind the wall. So I've seen Banach-Alaoglu theorem used without checking this, and that's a disaster. Okay, so you have to check that condition. Because this works, but the converse doesn't work, as I mentioned already. Now, the nice thing about Banach-Alaoglu is it tells you that this closed ball, the closed norm ball in X, is weakly compact. It's compact in the weak topology on X. That's super cool, okay, because it gives you the following conditions. If your feasible region is closed in the weak topology, and it's bounded in the norm, so it's closed and it's bounded in the norm. So what does that mean? I can make this U really big and fit your feasible region in it. So then it's a closed subset of a compact set, which makes it compact. So if it's closed and bounded, then it's compact in the weak topology. Sorry?
I'm just wondering, do we need totally bounded or something else?
No, I don't think so. No. Why would you need totally bounded?
Or you just get sufficient condition?
Yeah, this is sufficient. Yeah. You don't, that's not going the other way. Yeah. Now, this one is very interesting because, okay, when you learn about compactness in Rn, there's something called the Hani-Borel theorem, which says if a set is closed and bounded, then it's compact. And then you learn that's generally not true in other spaces. Bonnet-Alleglu kind of says it's kind of true. If you have the right setup, it's closed and bounded, then it's compact. But the key thing is that that's what this theorem statement is really confusing because it has the norm topology and the weak topology in the same statement. Okay, but if you can show it's weakly closed and norm bounded, I sometimes put norm to emphasize. You don't need norm because boundedness involves norm. But it involves two topology and you get weak compactness out of it. Okay, so let's continue with these results next time. Thank you. Thank you.
Oh, thanks, Mark. To show us like an example of like how they implemented linear program. He said that we wanted to be full. But the thing is, it's catchy there because yes, you need to define well the spaces, right?
So who told you that?
Some guy
It's on there.
Yes. He has a very, classical like foundations of
Yeah. No.
and that was shocking, like, because I was, I did some software analysis many years ago, so, but after that, I was trained with optimization, so then like someone telling you like, we've done this before, and you're like,
Well,
it's insane.
I think that, so the problem, and I'll get to that, we'll get it right here. Adjoint is the main person. You write that adjoint.
There might be a class.
Okay, we need to go.
I'm reading off on the one.
Yeah, it's good. The one you mentioned.
Here, okay, but we're gonna.
Yeah.
We're recording, so we're just gonna turn the recording off and it's all you.
I knew you had something to
That's
say.
it.
Yeah.